Welcome to the NC DWI Guy podcast, where defenders of the Constitution assemble to prepare for courtroom battle and firm owners gather to develop marketing strategies that will revolutionize the practice of criminal defense. Here's your host, the NC DWI Guy, Jake Minnick.
Hello, fellow freedom fighters, and welcome to episode 59 of the NC DWI Guy podcast. Today on the podcast, we have Dr. Andy Ewens. This is going to be a really helpful, informative episode. This begins our 5-part series on attacking the breath test. So Dr. Ewens will be back with us for episode 60 next week. We'll be kind of looking under the hood of the ECIR2 device during next week's conversation. On June the 16th, we will have James Nisi, DWI attorney out of Arizona, on to talk about DWI math. On June the 23rd, Matthew Davenport will talk about the per se implications and what does it mean, the language presumed impaired mean for purposes of, deemed sufficient. What does that mean when it comes to Nayron Simmons and to the statute on impaired driving? And then finally, on June 30th, we will have Stephen Lindsay on to talk with us about attacking the breath testing in closing arguments. So to give some general guidelines and suggestions on how to do that. Today, we're going to be talking with Dr. Ewens about understanding the science behind breath testing. And to give you a little background into Dr. Ewens' research and understanding of this area, Dr. Ewens is a PhD in pharmacology. He's a board-certified toxicologist. He has 25 years of experience in biomedical sciences. He has 15 years work as a government contract toxicologist. He's worked with organizations including the National Toxicology Program, Center for Disease Control and Prevention, the National Cancer Institute, the National Library of Medicine, and the EPA. He has 13 years of research experience. Some of his research has included developing curative immunotherapy for cancer in mice. He's conducted studies on SFST and DRE evaluations. He's conducted studies on CBD oil, on mouth alcohol. He's conducted studies on the smell of alcohol on the breath. And he has been qualified to testify as an expert on these type of issues in the courts of North Carolina, Texas, Maryland, and Michigan. So Dr. Ewens has an incredible background in this area, and it is very exciting to get your knowledge, Dr. Ewens, in understanding toxicology. So very excited to have you on. And I know that we haven't really talked before today, but we'll kind of kick things off and dive into the conversation on understanding the science behind breath testing. It's a pleasure to have you on the show.
Sounds good. Thank you for having me. I really appreciate it. My whole mission is to get the science right out in the courtroom. So.
I think that's really an important part. This is a 5-part series on attacking breath testing, and I think that it's really an impossible task to do that until you understand the science behind breath testing. I think there is so much of this kind of like black box mentality when it comes to breath testing, that there's just this kind of unknown what's happening. The test ticket prints out, what's going on in the machine is just this complete question mark. So trying to get the fundamental scientific principles behind breath testing, I think, is a really important first step in being able to successfully cross-examine, understand when you might need an expert witness involved on your case, understanding what's happening with your client in the intox room. So it's going to be fun to dive into these issues with you.
Yeah, I think definitely. And the whole black box idea with these machines is on purpose. The manufacturers make it very difficult to figure out exactly what they're doing.
Yeah, I agree. I think it is intentional. It's so hard to kind of be able to self-diagnose, to run tests on these type of devices. And so we'll kind of get maybe into some of the specifics of the ECIR2 in our conversation next week. But in terms of just understanding the science behind breath testing, I guess kind of an initial question that I would have for you is, if we're trying to determine a person's blood alcohol concentration, if alcohol impacts a person, impairs a person when it kind of reaches their central nervous system by getting through their bloodstream to the brain, why is it that we are concerned with, basically getting a breath alcohol concentration? What's kind of the connection between the blood alcohol and the breath alcohol?
It's a very great question because everything pretty much is an estimate. As you alluded to, the alcohol really has its effect to make someone impaired in the brain. In order to get into someone's brain, you would basically have to kill them or come up with some kind of scanning instrument, maybe like a MRI device or something,
Right.
that could possibly do something. But we don't really have the technology there. So what we do have is the next best thing, which is the blood. So the blood is supplying the alcohol to the brain. The alcohol is doing all its business in the brain. So the next thing we can get is the blood. The problem with the blood is that it's an invasive process.
Right.
You have to take someone to a hospital or get an EMT to do it. There are some jurisdictions where they have police who are trained phlebotomists. I don't know about North Carolina, but I know in some states they do have police phlebotomists. So they could take blood right out in the field. But then the other problem is you'd have to then measure it and wait for the results before you could use that as evidence to arrest somebody. So at the blood level, we're still using an estimate of what's going on in the brain based on concentration in the blood. In order to do field testing that can be rapid enough for an officer to use to make a decision to arrest, they went to look at the breath concentration. So here we've got the brain, the blood, and then now we're going to the breath. And each time you're jumping from one tissue to another, you're making assumptions, and it's really just an estimate as to what is going on.
Yeah,
so
I think that language in terms of estimate is really a critical thing, because that effectively is what is happening. As you've said, I didn't really ever think between the amount of alcohol that's kind of in the brain versus kind of in the rest of the bloodstream as also kind of being an estimate. But, you have that jump, but then going from blood to breath, you have a further estimation that is built in. And I think that that's one of the key things to really, in terms of how do you kind of bring this out in the courtroom, to walk through that process with the, whether it's the chemical analyst, the officer that's on the stand, or with an expert witness, to kind of walk through why are we even doing breath testing in the first place, to kind of get to that estimation language. Because I think it's important for the jury to know this is an estimate, so we can see when the person has a specific quantity of alcohol in their central nervous system, or estimating how much they have in the brain. So I just think it's a really important thing to bring out in the courtroom.
Yeah, and that's really the fundamental problem with all of this, is you don't know 100% what the alcohol level is, so you're just estimating it. So it's really just more for convenience of the police officer, that they can use that information in real time and make a decision on arrest.
Okay. And so in terms of the breath testing means of trying to estimate how much alcohol is in a person's blood. What is the science behind that estimation? How is it that we can kind of determine how much alcohol is in a person's breath to then give us an estimation of how much we would expect to see in the blood?
So it's based on Henry's law, which basically says that if you have a chemical inside a liquid, some chemicals will get out of that liquid and vaporize into the air. And if you have this in an enclosed system, so that the vapor that comes out can't just float away into the world, that eventually the amount of that chemical in the air will equalize with the amount of chemical in the liquid. Not to say that they'll be the same concentration, but that they'll reach an equilibrium where the rate of that chemical going into the liquid is the same as the rate of it coming out. And then you can measure that ratio between air and liquid of that chemical, in this case, ethanol.
Just to give kind of a quick mental visual of this, this is the same science that's used in blood testing, correct? When they do a test on a blood sample, you're basically kind of measuring, what's actually above the liquid sample in most of those blood tests. Is that right?
Right. When they do a headspace gas analysis, that's
okay.
That's usually done with a gas chromatograph. But I believe you can also do liquid chromatography on a blood sample as well, where it just uses the liquid portion of the blood and not the gas.
Okay.
So it can get past that.
But if you're doing it with a gas chromatography method, then what's happening is it's the headspace, the portion of the tube, so to speak, that doesn't have any liquid in it, that's being tested to see the amount of kind of alcohol concentration in the blood that's in the tube.
Right. And I think
sorry to cut you off. That basically, I just wanted to kind of get that mental visual in there in terms of the same thing is happening in a person's body with regards to breath testing.
Right. And I think that they primarily like to use the headspace gas for the blood testing because it's a real nice way of getting rid of all of the junk that they usually would have to get rid of. So the blood stays down in the sample. They're just picking up on what vaporizes off of it. Okay. So it's much cleaner than if they were to try to just measure the whole blood.
Gotcha. Okay.
But it is the same principle. But the problem is that this principle is based on a closed system where you've got a constant temperature, a constant pressure, a constant volume, and that doesn't really exist in the lungs. So you've got changing volumes, you've got changing pressures, you've got a change in the temperature where in reality, the temperature of the air that's coming into your lungs is not the same as the temperature of the blood that's going through the lungs. So that kind of alters it too. So the principle is that it's working. It's just it never really gets to the same standard as what the Henry's Law was measured based on, I guess.
Yeah, and I guess in terms of that kind of scientific principle of Henry's Law, with there being a requirement for kind of a space where there is constant temperature, constant pressure, can you kind of think of any other places outside of breath testing where that principle is applied in kind of a scientific setting? So Henry's Law, I can see a lot of this, happening again in a lab where they're basically, testing samples. They're able to, the lab technician, lab analyst is able to keep things at a very kind of measured pressure, measured temperature. are you aware of any other kind of places where scientifically Henry's law is utilized, where you're basically not kind of almost within like a lab space?
Not so much in a lab space. I mean, the EPA looks at this for environmental chemicals. So if you've got a chemical that's spilled into a lake or a river, you've got the chemical in that water going down the river, but you've also got some of it vaporizing out of the water.
Okay.
And so they can use that to look at how inhalation exposure,
Gotcha.
how much you might get if you're standing next to a river or something like that.
Okay.
But
yeah, I guess in terms of the principles as it applies to breath testing, that's one of the things that has always kind of seemed, a little bit like trying to fit a round peg into a square hole in terms of this constant temperature, constant pressure, using a person's lungs as your kind of space for applying those principles. So, in terms of the the changes or the variance in temperature and pressure, what is kind of the impact of that, in general terms, if you have a fluctuating temperature or pressure on the result that you're going to be getting?
So temperature, if you increase the temperature, that's going to make more of the chemical volatilize out of the liquid. So you'll get more of that into the air. If you were to change the pressure, increasing the pressure would actually drive some of the vapor back into the liquid. So that can have some effects. And the problem is how the problem isn't so much that these values change, because they just do in the lung. The lung, you breathe because you lower the pressure of the air inside the lungs. You breathe out because you raise the pressure of the air in the lungs. The problem is that when they do these measurements, they make assumptions as to what that person's influences are on the measurement. So whether you're in a closed system or not, there is a partition ratio, which is just what the Henry's law constant is basically saying. You've got concentration in the air versus the liquid, and what's the ratio between those two. You could measure that empirically without being in an enclosed system, but you then would have to say, that's what it is at this time right now, because I measured it. And with the breathalyzers, they don't do that. They'll say the average person has a breath temperature of 34 degrees centigrade. The average person has a partition ratio of 2100 to 1. And
can you speak to that just for a second? What does that 2100 to 1 mean?
So that means that if you have alcohol in the liquid portion, only 1 out of 120 ethanol molecules are going to be up in the air. So the vast majority is down in the liquid. Just a very tiny bit is actually in the air.
So basically, for every one, according to that, with regards to breath testing, for every 1 molecule of alcohol that you find in the breath, you could expect to find 2,100 molecules of alcohol in the blood.
Exactly.
Okay. All right.
So that's how they can make their estimations. They'll say, we'll measure this tiny amount of alcohol in the air. We'll multiply that by 2,100, and there's your blood alcohol concentration.
And I think, that multiplication factor seems to be important in terms of that ratio, because if for some reason, based on pressure or temperature or some other factor, you have slightly more alcohol in the breath than is kind of expected under the kind of normal person conditions, you then multiply that by 2,100. So, it seems like that would, potentially make a massive difference in terms of the alcohol that you're finding in the blood.
Exactly. And because of those that calculation, you know, if you get a little bit of alcohol, say in your mouth, that tiny amount gets blown up 2,000 fold. So
Right.
tiny differences make big differences in the measurement. And so the problem is that they're coming up with averages of what the partition ratio should be. And not everybody is the average. In fact, apparently the average human on the earth is a dead Chinese woman. So if we're not all dead Chinese women, then we don't all make that average. So really what they need to do is not take the average, but use a range. Well, the very most optimal thing is to actually measure what that is. But in order to measure it, you have to measure the alcohol concentration in the blood. So at that point, why do you even do a breath test anyway? But if you're not going to actually measure it, which the police don't seem interested in doing, then it's better to use a range of values to show that this is an estimate, so that the results from the machine aren't a single number, because a single number, someone's going to see that, a jury member, and they're going to say, oh, well, that's pretty convincing. You know,
Right.
They got one accurate number, but in reality, it could be a range of values.
And so in terms of that range of values, so basically that would be based on, again, the partition ratio. So if you are basing it on this, for every 1 molecule of alcohol we find in the breath, we expect to find 2,100 molecules of alcohol in the blood. What does that range look like? You kind of, at least in a, what would be kind of the general range where you could kind of expect to see maybe a higher number of molecules that would be in the blood, or a lower amount of alcohol in the blood? What would those numbers look like?
It's hard to really say exactly what they would be, because you can look at different studies, and depending on what study you look like, you're going to get a different range, because each study is looking at a different population of people, and everything varies. I mean, you can never be super certain of something in science. But in general, you could think of maybe instead of 2,100 to 1, maybe it goes down to 1,500 to 1, or maybe up to 25 or 2,800 to 1. It's just really hard to pinpoint and say, yes, we know 100% certain the range is this to that, because it depends on the study.
So again, just to kind of emphasize this point, because again, I think in terms of trying to be able to understand this, but then also communicate this to jurors in the courtroom, the partition ratio used in breath testing normally of 2,100 to 1 is based on the kind of non-existent average person. So it's just law of averages. You could potentially see a variant in terms of what the partition ratio would look like in this individual person. And so you're kind of suggesting it would make potentially more sense than to use a range of results that are based on those kind of like, extremes at either end of the spectrum of potentially 1,500 to 1 up to maybe 2,800 to 1. So you could see what the possible differences would be based on the individual person.
Right. And it's what I'm saying about the difference in different studies, getting different results, is that trying to come up with that range that you would use in a calculation is really difficult.
Right.
Because you don't want to get too far in the extreme. You want to keep it, at a likely result, but then, you can find a study that'll say something way out there.
Right. Yeah. And I think, obviously from a scientific standpoint, in terms of trying to understand exactly what the breath testing is doing, that range is helpful when it comes to the evidence getting presented in the courtroom, one thing that I've kind of talked to in terms of the jury is we've got to assume kind of the partition ratio that is, gives the benefit of the doubt to my client, because you're required to find my client guilty beyond a reasonable doubt. And so we kind of have to assume best case scenario for my client when it comes to the standard of proof that's being required in the courtroom. So in terms of those ranges that are being utilized, again, because the jury is not being asked to convict the average person, but the individual person, and they have to find that the evidence shows guilt beyond a reasonable doubt. That's where I think instead of using the average, my kind of communication to the jury has been, we should use the partition ratio that would be most conducive to my client. That would be kind of give the benefit of the doubt most to my client, because we don't know what the partition ratio is in, this particular person.
Well, usually how I do it is I've got to look at it from the science. So I'm not looking on one side.
Right.
So I'll give the full range, whether it helps the client or hurts the client. But then when you compare that, say instead of the machine coming back and saying you have a 0.08, you're going to jail, it's a 0.06 to a 0.10.
Right.
Just the fact that the range doesn't all go above 0.08 is reasonable doubt right there.
Exactly. That's,
it's okay.
I think from a scientific
over.
perspective, in terms of the testimony that you'd be offering in the courtroom, using that range is helpful, because again, it just shows here's what the real science looks like behind this, as opposed to just using this average. And then the defense attorney can really then hammer that range in terms of if there's anything below the legal limit. It's kind of like, well, we've got to take this into account in this particular circumstance, because we don't know what the actual partition ratio is in this person. So I think that's really helpful.
And like what you're saying, what would probably happen is on direct exam, I would be asked about the low end of the range, and on cross exam, I'd be asked about the high end of the range, depending on what they want to pull out of that.
Yeah, I think it's better to just ask about the whole range. I mean, if in direct, if you're asking that from a defense perspective, because could it have been higher? I think that doesn't really hurt the defense at all. The real question is, could it have been lower? Because most of the time, we're not arguing this if the result was less than 0.08, right? We're hopefully not going to be going too far down this road. But I think that having that full science, I mean, I think that one of the things that jurors are left with when it comes to breath testing generally is that they don't get a whole lot of science about it, right? It's basically just, did you run the test? Did you push the buttons? What was the sheet that came out? So anything that is happening in the process of capturing that result is, I would say, 9 times out of 10, never even discussed in the courtroom. There isn't any kind of explanation to the jury about how breath testing is working. So I think as much information as they can get on that front, that they can actually sink their teeth into, that's going to be helpful for the defense.
And if you go ahead and compare it to like a blood test, the blood tests are going to say, this is the value plus or minus whatever it is. But the breathalyzers don't do that. So
yeah, that's a good point. Yeah, I mean, so on any lab result that you get back, you normally see a range of, plus or minus 0.02 to 0.04, just depending on what the result is. That's a good point, that there's no such kind of like similar, kind of range of results given on a breath test.
Right. And so, the reason that these are different can range from different things. Someone could have a fever one day and raise their temperature so that more ethanol is being vaporized. One of the interesting things is the state requires the reference standards for the breathalyzers to be run either on a dry gas sample or a wet bath, which is basically just glass jar where they heat up water with the alcohol in it. So they specify, the state does, that this has to include distilled water with the alcohol. The problem is the partition coefficient depends on basically two main things. How volatile that chemical is, which usually depends on how small it is. You know, if you've got a big giant molecule, it's not going to float up in the air very much. Little ones like ethanol, they speed around and they can zip up into the air. But then it also depends on the solubility of the chemical. Ethanol has a hydroxyl group, which is very polar, and that interacts with water, which is also very polar. If you alter the solution, the reference solution that you're using in your wet bath simulator, you could alter that partition coefficient. So the state says you just run distilled water, but blood is not distilled water. It has salts, it has proteins, it has lots of different chemicals, it has cells. All these things could alter that partition coefficient. I did a quick little study, nothing that I'd be willing to publish yet, with my ECIR2. And if you add salt to this distilled water, it will increase the breath alcohol concentration. If you add fats to the water, it will actually decrease the concentration. So if the person's dehydrated, their concentration of salt is going to go up, and they could have a higher blood alcohol level or breath alcohol level. If they've just eaten a big meal, especially like a fatty meal, that could actually decrease it a little bit.
Okay.
And I looked at sugars, and so far I didn't see that sugar made a big difference. But still, you've got changes in the partition coefficient that could be based on what someone ate, any medical conditions, if they're taking drugs like diuretics, that can change the salt concentration. You've also got the temperature component. Not only is every person running at a different body temperature, but that body temperature changes throughout the day. So we've got hormones that regulate the circadian rhythm, and your body temperature goes up during the day, and then as you go to sleep, your body temperature decreases. So it's constantly changing. So that partition ratio really never stays the same. Plus you could, I haven't looked this up 100%, but I'm pretty sure you could have different disease states such as emphysema that would lower the partition coefficient, or other pulmonary diseases, pneumonia, things like that, are going to alter that.
And so again, in terms of like just the reason why that kind of temperature issue is important is that because the device assumes that a person's body temperature is going to be approximately 34 degrees centigrade, if there is a increase in temperature or a decrease in temperature, that could then impact the actual alcohol concentration that's being reported.
Right, exactly.
Okay.
And it's really kind of weird because they focus on the breath temperature, but it's more complicated because the breath is going to be cooler than the blood temperature. So you never really have that 100% equal temperature. So, you know, ideally you would measure a person's breath temperature and their body temperature and then use that to go into their calculation, but that's not done.
Yeah, I think that's an important thing to bring out. When I was kind of looking through the ECIR2 manual, they kind of emphasize in the manual how important it is that the sample itself be kind of introduced at a certain temperature. So the device is supposed to basically heat up the chamber so that it does kind of capture that at the right temperature, and how important it is, what, you know, the impact would be if the alcohol concentration was lower, or I'm sorry, the temperature was lower or higher.
Right.
So again, you know, this idea of there being kind of a constant pressure and temperature, and they kind of relate it back to Henry's law, is important, even from the state kind of being able to do a valid accuracy check, so that, you know, they kind of have that built into the manual itself.
Yeah.
So I guess in terms of just kind of maybe understanding a little bit about how you know, some of the more recent breath testing devices work. The ECI R2 uses basically infrared system to test, as well as a fuel cell. Can you just talk a little bit about what's going on in terms of the purpose of the fuel cell and the purpose of kind of the infrared system? What are those things looking for when it comes to the breath sample?
So when I first just heard about the breathalyzers and how they worked, before I knew enough to look into them, I thought this was great. They've got a infrared spectrometer, and, you know, in the lab, you use infrared spectroscopy to identify what a chemical is, and you can basically say that is, you know, if done right, that is chemical XYZ. We know it because this infrared spectrometer. The problem is these don't have that. They use an infrared system, but it is not a spectrometer. It's not even close. So the state crime lab says in their SOPs that you need to have a reference standard of what chemical you're looking for, and your sample needs to match that with 6 different peaks. So let me back up. The infrared spectroscopy, or infrared detector, it takes the breath and it shines infrared light at various wavelengths. And some of that light, depending on what wavelength it is, will get absorbed by the alcohol. So the carbon and oxygen bonds will absorb a certain wavelength, and it causes them to stretch and twist. The oxygen-hydrogen bonds will bind a different wavelength, and the carbon-hydrogen bonds will bind another wavelength. And each time it does that, it absorbs some of that wavelength out, so that when you measure how much light reaches a detector after it's gone through the breath sample, it should be lower when there's alcohol present at those specific wavelengths. So when you're doing infrared spectroscopy in the lab, you look at all the different wavelengths that you can, and where a chemical will absorb a certain wavelength, you'll get a little peak, and then where it doesn't, you'll just get a flat line. So the state crime lab says that you have to match at least 6 different peaks with a known reference standard in order to identify that chemical. And they really should be not just you're getting some absorbance at this wavelength. It should be like peak 1 at this wavelength is twice as big as peak 2 at this wavelength, which is maybe a quarter or 4 times the peak at this wavelength. So it's also the ratio and the patterns of these peaks. The way the breathalyzers use this, they only
and that would be
wavelength.
used, those six peaks requirement by the lab. Is that kind of in regard to like blood testing? Is that what you're?
Well, it's more used for like looking for a powder to tell if it's cocaine or something like that. So it's not really used in the same way, but just talking about how you use that information. when you've got
to make
that
sure that
full
you're
spectrum.
identifying the correct chemical.
Right.
Okay.
So to do that, you really need this full spectrum to look at all the peaks that are possible. But the breathalyzers, they only use one wavelength. They'll just pick one of those peaks and say, that's alcohol. And that's just not how science works. You can't identify anything on just one peak because there's lots of different chemicals that would have that same peak. So when I originally heard about these, I thought the infrared spectrometer, that means these things are going to identify alcohol and be able to separate it from isopropanol and acetone, which can be caused by diabetes, but that's not how they do it at all. So their main detection system is a fuel cell. A fuel cell, I know maybe 10 years ago, was looked at as the next generation of a car, that it could be, you could have electric cars and they would run off of fuel cells. So basically what these are is a sandwich of two metal catalysts separated by an electrolytic fluid, so a fluid that ions can pass through. So on one side of the sandwich, the alcohol is exposed to. These breathalyzers use a platinum catalyst, and so they're going to bind to this platinum, and the alcohol is going to get converted to acetic acid or vinegar. Then that's going to produce some electrons that can flow to the other side of the sandwich plate, so the other metal part. And those electrons are going to be given off to oxygen in the air, and that's going to create water. So you're getting this chemical reaction separated by this fuel cell, and the chemical reaction produces electrons that are going to flow from one side to the other, and that electron flow is measured as an electrical current, and that's supposed to indicate the amount of ethanol that's there. The problem is these are metal catalysts, which can react with lots of different chemicals. And a lot of the manufacturers will claim that it's the specific characteristics of their fuel cell that makes it react to ethanol and not other chemicals. And that's really not a good way to specify a certain chemical. So really, this would be thought of as a screening method in science, based on the fact that you're not getting any information about that chemical. All you're getting is information that some chemical reaction is occurring and it's producing an electrical current, and that's it. It doesn't tell you that that's ethanol. But the manufacturers will claim that, it's specific for ethanol.
Yeah, I guess that in terms of the number that is kind of generated from that sample that's collected and tested by the machine, is it the fuel cell or the infrared system that is giving the number, or both? How is where is the number being generated in terms of the actual alcohol concentration?
The number's being generated by the fuel cell.
Okay.
And they really put all their focus on the fuel cell.
So the infrared is more just kind of to confirm that alcohol is what we're dealing with. Is that a good way to think about it? Or what is the infrared system doing in addition to the fuel cell?
That's what I thought, and that's what I hoped, but that's not it.
Okay. Okay. Gotcha. Okay. That's what it's supposed to be doing, is confirming that this is the chemical that we're dealing with, is alcohol specifically.
Right. If you were going to do this to make a useful, helpful instrument, you would have it a full spectrum infrared and then use that to say, yeah, that's ethanol, versus no, that's acetone, the person's a diabetic. But since it only looks at one wavelength, you can't do it. So what they use this for is because there's a limitation in the fuel cell. And the fuel cell's limitation is that it takes some time for this chemical reaction to occur. And so what they need to do is, as you're blowing into the instrument, they need to grab a sample of that breath and allow it some time to react with the fuel cell to get the measurement. So what the infrared, I won't even call it spectroscopy, the infrared detector does is it measures how much it thinks alcohol is continuously. So as soon as you start blowing, it's going to start picking up some ethanol. As you continue to blow, it's going to measure and tell you if the concentration of ethanol is increasing or decreasing. And then once you reach certain preset parameters, like blowing a certain volume of air, when you start to see the concentration of ethanol in the infrared detector level off, then it says, oh, that means that the air is deep lung air. It's close to the alveoli. And so it's the most accurate air to measure. And then it triggers the fuel cell to grab a sample of that air and test that. So it's really just a way to do two things: to make sure that the fuel cell is sampling the air that comes from the deep lungs, and then two, it tells if the alcohol concentration is increasing or decreasing as you're blowing. And that's important because if you have alcohol in your mouth, what will happen is as you start to blow into the machine, the concentration of alcohol will be high right away because that air inside your mouth is going in first. And then it'll start to decrease as more air from within your lungs starts to dilute out the air that's in your mouth. So this is called a slope detector. So if the infrared detector sees an initial high alcohol and then it starts to drop down, it will give a signal that says mouth alcohol, you have to repeat the test. What it wants to see is that the alcohol concentration goes up because you're just getting ethanol from deep within the lungs. So the infrared detector really makes it sound like it's more sophisticated than it really is. It's basically just a fuel cell detector.
Okay. Well, and I guess, in terms of kind of bringing that out into the consideration of the jury, I think that kind of explanation is going to be really powerful in terms of them being able to understand, again, exactly what the device is doing. So kind of walking through that with pictures, with an explanation of kind of, what the device is measuring, how it's kind of getting to this specific number. I think kind of an explanation, again, of that science behind it. What is the infrared system doing? What is the fuel cell doing in terms of converting alcohol into, basically these electrons that can then be measured, getting to a specific number, and then going through all of the various ways that could then basically be a kind of a number that is based on some sort of kind of misdiagnosed information by the device, kind of going through all of the different possibilities.
Right.
I think that's a really helpful thing for the jury to be able to kind of take that in.
Well, I think with all of the drug testing tests that are out there, you have to realize that they sound very sophisticated, yes, and super accurate, but they all come down to basically an electrical signal. And that's it. All they do is they give you an electrical signal. And it's, how did they get that electrical signal? What does that mean? That's really important. If they'll say, yeah, this is a false positive test, and I can show that because of X, Y, and Z, well, they could come back and say, well, How do you know it's false positive? Or how could it be false positive? Well, because all you're giving me is an electrical signal. That's it.
Right.
That's all these machines do.
Yeah, and I think that's important. Again, in terms of even the jury understanding where this number comes from. If all you are kind of doing is kind of taking a electrical signal to generate then a specific numerical concentration of alcohol, kind of working almost backwards through that process at some point to saying, there's alcohol that's in the brain, is in other parts of the blood. We estimate how much is in the breath. If going from the breath into the device, that could be impacted by how much alcohol is in the person's mouth, the person's temperature, what the specific sample that's being blown in is. Are we getting deep lung sample? Are we not getting deep lung sample? And then going through kind of what's happening inside the device and the fuel cell. How is this being measured? How is the alcohol being broke down to then be able to be kind of numerically generated into this specific result that is printed out of the machine? I think kind of going through all of those different places to kind of show, we're kind of estimating, using assumptions, all of those different things then can kind of be used to kind of show here again is where there could be issues with a false high positive, or on the flip side, maybe a false low result. I mean, either way, there's an issue in terms of what the actual result would be coming out of the device.
Yeah, and I think that's a really good point you just made. I mean, you really want these to be as accurate as you can, because you don't want to also miss somebody who is impaired.
Right.
Just like police body-worn cameras, record the evidence because it helps both sides, because we actually know what happened. We're not just guessing at what happened. Same with these. You want it to be as accurate as possible so that, maybe you are making more arrests, or maybe you're making less. But that the information you're getting about their blood alcohol concentration is more correct than it was in the past. I mean,
exactly.
That would be good.
Yeah, and I think maybe to kind of close the conversation today, I think it is a really powerful piece to be able to bring this out to the jury. And I think it's difficult in a lot of ways to do that without an expert witness, because as much as you can cross-examine the officer that is involved, the chemical analyst that is involved, they have no chemistry background. There's no ability to kind of diagnose. Most questions that I'll ask officers about the workings of the ECR2, even if they've gone through the training to become chemical analyst and kind of gone through the course, it's basically like, this is above my pay grade. I don't really know how this device functions, or how, I'm just trained to operate the machine. So what do you think would be kind of some of the value in having an expert witness to be able to communicate kind of the scientific principles of breath testing to the jury?
I think it would be that you're letting them know that there is variation in these machines. There's nothing magical about them. And even more so that because they are a black box, they should be even more skeptical about what's going on inside them. I know it's been a hot topic for a while that manufacturers are not letting anybody know the programming of these instruments, and that they've been sued over that, and they still refuse to let people know what exactly they're doing inside that instrument. So I think, just like with any defense, you're looking to show reasonable doubt, and unfortunately there is doubt, because instead of this machine saying your blood alcohol is this, you're saying we've estimated that your blood alcohol is this, and it never comes out that way. And I think they do that on purpose, probably. That's why they're not reporting a range of error in their instrument. They're just giving a one result.
If you found the information in this podcast to be valuable, I simply ask that you pay it forward and share this podcast with another member of the legal community. Also, if you would leave us a rating or a review on whatever platform you are listening on, I would greatly appreciate it.